Well, hello. A number of mechanical engineering undergraduate students are interested in automotive engineering. Some are interested in gas turbine engines, either let's say for aircraft applications or stationary applications in power generation. I think all of this interest is just great. And chapter 9 in your textbook has to do with what we call air standard cycle analysis, which applies to both of those categories of engines. And when you start doing your homework problems, there's going to be some jargon that you encounter in the problem statements that may confuse you. And so what I want to do is give you a little introduction of what we call air standard or cold air standard cycle analysis for these type of cycles. So let's get started. And so I've taken a little clip out of the beginning of chapter 9, introducing engine terminology. And so what I want to talk about and give you some guidance on today and some tips would be when you're reading a homework problem and you see the phrase air standard, or you read a different problem and then you see the phrase cold air standard. What's the difference between these two? So I'm going to try to give you a little overview of how these two are similar, how are they different, why use these types of analyses, and when to use one or the other, and what are the key solution approaches for both of these types of standard cycle analyses. Okay, so I've taken some screenshots of two different homework problems that you may be assigned. Let's look at 9.9. It says an air standard auto cycle, blah, 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 blah. And so he said, okay, I'm ready to solve this problem, but what does air standard mean? And then you may be assigned problem 9.10. And it says, consider a cold air standard auto cycle. Well, both of those have to do with something called the Otto cycle. That's the model of a spark ignition engine in your car, okay? But we've got to understand before you can start putting pencil to paper, what's the difference between air standard and cold air standard analyses? They are both similar, but also some of the solution steps are different. Okay, and so I'm trying to create a little decision tree for you. So when you read either air standard or cold air standard, let's see, the substance is the same. It's air. It's that mixture of nitrogen and oxygen, similar to the dry air that we breathe. And so our model for the substance is the ideal gas model. And we'll, in here in just a second, we'll talk about those basics for any ideal gas. Then you've got to make a decision. If you see the words air standard, your model for specific heat is going to be variable specific heat. Now, what that means in terms of physically, what do? What variable specific heat and air. Variable specific heat and air, that means use table A22 to look up the properties, enthalpy, internal energy, and some others. Let's see. Okay, so that's air standard. That's the recipe for when you see air standard. When you see cold air standard in the homework assignment, okay, you still got the substance air. You're still going to model it as an ideal gas, but the nice thing is you're going to be able to model the specific heat as a constant number, and that can simplify a number of your computations. So what does that mean? It says for property changes, let's say like internal energy change, enthalpy change, what you're going to do is you're going to go to table A20, look up air, okay, and you're going to select a single constant value for specific heat, either C sub P or C sub V, or whichever one of those you need. That's the recipe. You read air standard, you're using table A22 for air properties. You read cold air standard, you're going to go and you're going to select a single value for CP and or CV. and then move ahead from there. Okay, so why are we talking about air standard? Look, these are just screenshots of classical engine cycles that you're going to have the ability to analyze the performance of these engines yourself. You're going to gain that ability. That's a very powerful computational ability to, given certain key parameters of these engines, what's the thermal efficiency of the engine? How does that engine convert heat into power or heat into work? Okay, very powerful engineering ability. So here's a couple of images. Let's see, I believe this one is a diesel engine. Okay, here's a spark ignition engine that we model as the Otto cycle. Here's a picture of a turbojet engine. Okay, here would be a picture of, well, of course, this is a propeller-driven aircraft, and so it's going to have a gas turbine engine that is producing net power, and that's what's driving the propellers. Well, here's the exhaust of a turbojet engine with its afterburners on, and then here's a cutaway cycle of a small internal combustion engine that would be operating on the Otto cycle. That's why you're interested in getting good at cold air standard and air standard analyses. Okay, so cold air standard. Commonly used for these types of engines where the inlet state is ambient. Inlet state is ambient, just like one atmosphere, ambient temperature. That could be an example of where you're assigned to use the cold air standard. So the inlet state of this engine is atmospheric pressure at sea level and temperature at sea level. Okay, here's some examples of where the inlet conditions to the engine would definitely not be ambient, correct? Aircraft flying at high altitude, clearly not 1 atmosphere pressure, less than 1 atmosphere pressure. Okay, and there's a cutaway of a gas turbine engine. This is a turbofan gas turbine engine that would be used to power, let's say, Boeing 747s, very large engines. Okay, so anyway, you get the idea. When would you use cold air standard? When would you use air standard? So your job is to get good at both. Let's review what kind of basics do we have for any ideal gas? Doesn't matter of neither air standard or cold air standard, any ideal gas. What do you know already? R bar, you know, you've committed to memory. R bar is 8.314 kilojoules per kilomole degree K, and R bar equals 1545 foot-pounds force per pound mole degree R. That's the universal gas constant. So whenever you need to determine R, the gas constant for a specific ideal gas, you're going to go R bar over the molecular weight. It is my hope that you've got memorized in your head the molecular weight of dry air is 28.97 kilograms per kilomole, which exactly equals 28.97 pounds mass per pound mole. That gets you started on your analysis. What's the next thing you know? What comes into your head about any ideal gas, including air? Ideal gas equation of state. So you say, well, wait a minute, where's that PV equals MRT that I know? Well, that would be for a closed system, but let's just say in general, either closed or open system, P times little v, specific volume, equals RT, or little v equals RT over P, or rho density equals P over RT. All of those you know by heart, and the way you use them depends on the analysis. Okay, all ideal gases. So for all ideal gases, the enthalpy and the internal energy, H and U, those property values depend only on the temperature of the ideal gas, not on the pressure. Okay, so we can simplify that general definition to say Cp for an ideal gas is equal to dH dt. And also C sub V is du dt. So that's an ordinary derivative, du dt, and dH dt, ordinary derivatives. Another thing you know by heart at this point is that whether CP and CV are variable or constant, when you subtract CV from CP, in other words, CP minus CV, it always equals R, which is a constant. It's another neat outcropping for any ideal gas, including air. Okay, so let's summarize. You know the universal gas constant. You know how to compute the gas constant R for any ideal gas, including air. Okay? You know the ideal gas equation of state by heart. Okay? And you also know the definition of CP and CV for all ideal gases. Another thing you know, oh yes, okay, K. K, so little k, that's defined as CP over CV, okay? And when is K constant? When would K be a constant? K would be a constant whenever CP is a constant, right? Because K is CP over CV. So the only way to force K to be a constant is for C sub P or C sub V to be a constant. All of this you should have in your head. Okay, so now we're getting into computational details so you can get good at analyzing these engine cycles and getting your homework done. Okay, so let's look at the left column of the slide. You've been given air standard, and your job is to calculate either change in enthalpy or change in internal energy, depending on what you're analyzing. Well, what would you do for air standard cycle? That's variable specific heat. Well, you're going to look up individual values for H or U in table A22 as a function of temperature. And we'll look at a screenshot of that table in a second. But remember, T is tabulated on the left-hand column, and you're simply going to look to the right to look up a value for H or U. Okay, let's move over to cold air standard for finding the differences in H2 minus H1. Wow, that's really pretty easy. H2 minus H1 is simply C sub P times T2 minus T1. It's the integral of Cp dt, where Cp is constant. Similarly, U2 minus U1 is simply Cv times T2 minus T1. And so in these analyses, you're always trying to find changes in enthalpy or changes in internal energy. You're not trying to find what is H2 or what is U2, what is U1. Typically, you're always looking to find changes in enthalpy. Okay. Let's say, for example, you're faced with needing to find change in entropy, S2 minus S1. That's another common need in this analysis. Let's look at the air standard, where we're modeling air as an ideal gas with variable specific heat. Well, what you're going to do is you will refresh your memory or seek out in your book. Let's look at the bottom line first. You're seeking to find S2 minus S1. Well, you seek this out in your book, you'll see that it's equal to S02 minus S01 minus R natural log P2 over P1. Now that's derived from one of the TDS equations, but let's not get into that right now. Let's drive towards your computational approach, okay? Well, this one's going to be, you're going to know P2 and P1. You've already gotten R, so this part of the computation is easy, but this S02 and S01, those are lookup values from table A22 as a function of temperature. Okay, so that's your approach for the air standard analysis. You're using table A22. For some reason, you need to calculate S2 minus S1, or maybe you need to equal 0. What if S2 minus S1 is 0? What does that mean? That's an isentropic process, and you're going to be analyzing a lot of those in these homework problems. All right, well, anyway, you get the idea. You've got to look up S02 and S01 separately in table A22. All right, let's move over to cold air standard, ideal gas, very constant specific heat, and you're trying to find S2 minus S1. Well, this is where you're going to go into your book and look up these two critical fundamentals that you can derive from the TDS equations. One or the other of these will apply to your particular problem. And look how easy it is. Typically in these analyses, you're going to know T2 and T1. You're going to know either P2 over P1 or V2 over V1, depending on the engine you're analyzing, depending on the model you're analyzing. So do you see how it's easy then to calculate up S2 minus S1 for constant specific heat? Okay, here's that promised screenshot of table A20, okay? This is where you have constant specific heat, and you need to select a number for C sub P or C sub V or both. Well, what you'll do is in the problem, it'll specify what is your ambient temperature. You'll go to that ambient temperature or whatever temperature it says to evaluate the C sub P value or CV value at, and you will look up that value. Might have to interpolate, but that's what you're going to do for constant specific heat, table A20. Let's take a closer look at table A22. Ideal gas properties of air. So this applies only to air with variable specific heat. Well, here's the left-hand column, T. Notice here, table A22, it's sort of got two blocks of table. Okay, so recognize the two blocks of table. We start out really, really cold. That's low temperature, and temperature increases until finally you got to swap over to the right-hand side and keep going up with your temperatures here. Okay, a lot of students overlook that, all right? Well, how about if you need H or U? Simple lookup, right? H or U as a function of temperature. If your temperature's it's nearly a no-brainer. You just write these numbers down. And if you're trying to find H2 minus H1, you just subtract one for the other. Very special thing that I need to point out that you need to be aware of. Look at these columns and look at the column headings, PR and VR. Notice above those it says when delta S equals 0, and that little footnote 1 that applies to simply the reference, the academic reference for the data. Okay, but it says that when delta S equals 0, so these two columns, PR and VR, these values only apply to processes that are isentropic, delta S equals 0. Be very aware of that, PR and VR. A little bit more about PR and VR shortly. Okay, I hope you got it. Now, since I just mentioned about this S0 value and only applies to isentropic processes, let's look at the details about analyzing an isentropic constant entropy process. For this example, state 1 to 2i. It's an expansion process. Pressure's dropping. 1 to 2 isentropic. 2i, 2 isentropic. Okay, that's our example problem we're going to look at. We're going to look at variable specific heat and constant specific heat computations. Okay. Air standard. Air standard, that's where you have air as an ideal gas with variable specific heat. And our job is to determine T2i. That's where we're headed for our analyses, as always, determine the final temperature. What's T2i? Well, so what we'll do when we've got variable specific heat is we're going to go to table A22 and we're going to use the relative pressures, PR. Okay. And let's see. I'm not sure. It looks like I have not given enough details on this slide, but I think maybe I will moving forward. But you're going to be using table A22 for, oh, well, let's see. Maybe I can explain it. Notice how if you have T1, do you see that you can look up PR1? You'll do that, okay? And you will have P2. Think back about the sketch. Here, P2 was given, all right? What I didn't put on the sketch was that there's a special relationship for ice entropic processes, and that is PR2 over PR1 equals P2 over P1. So I don't have it on the slide, but just think what I said. Okay, you have P2 and you have P1. That's the right-hand side of the equation. You just looked up PR1. Multiply both sides by PR1 to solve for PR2. Okay. Wow, I just found a numerical value for PR2. I'll go back to table A22. I will look for that number in the PR column, and then I will back solve for the temperature, T2I. So I'll have to apologize. I didn't have that fundamental on my slide, okay? But that's the way you do it for variable specific heat. Let's flip over to cold air standard, constant specific heat, okay? Well, our job is to find T2I. What we will do is we're going to recall that for an isentropic process with constant specific heat undergoing isentropic process, ideal gas, PV of the K is constant. And you can derive a solution to solve directly for T2 isentropic. Now that I'm thinking ahead, I think the next slide may disclose both of these processes, so it won't be so confusing for this PR stuff. So let's go to the next slide. Okay, looks like we're going to treat cold air standard first. How do you work with PV of the K as constant and then solve for T2 isentropic? Here's how you do it. Okay, so PV of the K is constant applies to ideal gas, constant specific heat. In other words, K is constant, undergoing an isentropic reversible adiabatic process. And here is the derivation. I know you're going to be driving towards the final result, but let's breeze through the derivation. PV of the K is constant. That means P1V1 to the K equals P2V2 to the K. You should be able to derive this on your own, but I know you want to drive towards the final result. Let's replace V with RT over P. Okay, so here's the algebra. I've replaced V with RT over P for both state 1 and state 2. Okay? The next thing I'm going to do is a little more algebra, and I'm going to simplify my equation to say P1 to the 1 minus K times T1 to the K equals, it looks like I have a typo. That should be P2 to the 1 minus K, T2 to the K. I'm going to have to correct that, okay? We will solve for T2. So T2 equals T1 times, my mistake, P2 over P1 to that quantity to the power K minus 1 over K. So there you go. That's the way you solve for T2I using the cold air standard isentropic process, constant specific heat. Okay, now I'm disclosing this variable specific heat approach using P sub R values from table A22. Okay, and here's what I said in words here a minute ago. PB over PA, so that's just like P2 over P1 equals PR sub B over PR sub A, where B is like 2 and A is like 1. Okay. Similarly, that's where you have your pressure ratio. Let's say you have a problem where you have your specific volume ratio instead. That's commonly you have that for internal combustion engines, like a diesel engine, okay? Well, so the same thing, same applies here. VD over VC, that might be like V3 over V2 equals like, kind of like VR3 over VR2, okay? Where VR is a function of temperature only. And so I hope that you get the idea. I hope this clears up my blabbering on about how to solve for T2I. I'll try to make that correction on my P2, P1 blunder. Okay, So we've covered some of the analysis details if you're assigned to do air standard or cold air standard analyses. How are these two things similar? They are similar because you're analyzing a power cycle using both of these models for an ideal gas. And so a quick memory refresher, cycles. Typically for internal combustion engines in this class, such as the diesel, Otto, and dual cycle models, you're going to be analyzing one single cycle that you can draw on a pressure volume diagram. For a gas turbine engine model, which is the Brayton cycle model, you think about the way a gas turbine engine works. It's a set of steady state, steady flow open systems. There's 4 components, and they're all tied together and operating at a steady rate. And so you're going to be analyzing steady state, steady flow open systems. You're going to be drawing a TS diagram to visualize that process differently than the internal combustion processes. But look, on both of these, on the Brayton, the diesel, the Otto, and the dual, you're going to be asked in the problem statement to analyze it using the air standard model or the cold air standard model. Okay, so what's our recap of this intro? Air standard means air is the substance, modeled as an ideal gas with variable specific heat. And so translation, use table A22. Cold air standard model, air, ideal gas, but constant specific heat. C sub P and or C sub V are just a constant number, and you will go to table A20 to determine what is that constant number. And so what I want you to recognize is the process by process analyses, 1 to 2, 2 to 3, 3 to 4, 4 to 1. Each of those process analyses really are the same fundamental equations. All you're doing is using property evaluations that are different with 2 different specific heat types of models. I hope that helps. Okay, so I hope that helps you get ready to do your homework problems, or if you get stuck or if you need some guidance, I hope that clears that up for you. So good luck with solving all of these cycle analyses problems in Chapter 9. They're very powerful, and they can really get you set up for a good, successful engineering career once you get that degree.